Yeah. Professor Jean-Claude Morel, can you share your screen?
Yes.
Yeah, I will do a short presentation.
Yes.
Professor Jean-Claude Morel studied at the University of Grenoble in France. He was a researcher for the French Ministry of Sustainability at the Ecole Nationale des Travaux Publics de l'État of Lyon. Before joining Coventry University as a professor low impact buildings. His current research activities include sustainable building with earth and stone. He has more than 50 articles in peer-reviewed journal, co-writer of 7 books. He is editorial panel member of the journal Engineering Sustainability of ICE. So please start your presentation, Professor Jean-Claude Morel.
Yes, can you see my screen?
Yeah, very good.
Okay, thank you. Thank you for inviting me to this conference. I'm going to talk about RAMDUF, but soon I will show why RAMDUF can be used to reuse crushed concrete or waste from concrete. But mainly my presentation will focus on why RAMDUF is designed to fulfill the circular economy principles in the construction sector. So the next slide was about my presentation, but as Professor Bao Bui has presented me already, I shifted this one. And so the plan of the presentation is in 3 sections. First, what is earth construction and earth and architecture? I'm going to talk about different levels, different scales, about this material scale, and the architecture scale, so the building, the asset scales. Why is it interesting to use the earth as a construction material? The section 2 and section 3, it's more focused on the circular economy context, why it is very useful to go for this approach in the circular economy context, and then the conclusion. Okay, so first the material. I'm going to talk about earth, but actually it's simply a soil. And so soil means that you may have clay, silt, sand, gravel, and stone. And clay, in our case, is the binder. Okay, and then the other grains are the granular skeleton. So if I'm talking about binder, it's to make a parallel to concrete. But this binder is natural and it's clay. I'm going to talk about unstabilized round earth. There's another type of round earth. We call it stabilized, and usually stabilized with cement. It's a very different approach because the architecture must be different, the costs are different, and so on. So I'm just going to talk about unstabilized round earth because my focus here is also to show that it's possible to use crushed concrete as an aggregate to reinforce this type of material. There are different type of earthen construction material. There's also compressive block, CEB. They are also manufactured by compaction, and it's like units, masonry units. There's some different type of approach called COB in English. It's not masonry unit, it's a massive wall made on site and in a plastic state. And adobe are also another type of techniques. It's small units, masonry units, and similar process to cob. There are much more techniques in earth construction, but just to show you the variety of techniques, I'm not going to talk about them all. Earth is a natural nanomaterial, and we can see we have different size of grains, and we have also macropores. And the clay particles are the smallest grains. If we can talk about grains, it's actually sheets. So it's the nanoscale sheets, and those different size of grains and clay sheets are generating different size of pores. And different size of spores will manage to generate some capillary forces, because then there will be always some water inside this porous material. So different scale of study, if you want to have a view on this material, it's very similar to concrete in a way, with those different scales. We usually give the characterization of the soil with the granulometry, and here you have different. You have two different soils, different earth. So sorry, it's in French, but you can see the size. The x-axis is the diameter of the grain, and the vertical axis is the quantity of those grains. So two different earths here, they were used for rammed earth in the vernacular architecture. And usually in soil mechanics, we are considering that clays smaller than 2 micrometer as a particle size, but actually this threshold is not accurate at all. So it's very difficult to quantify the clay content of those soils. But what we know is that it's necessary to get enough clay to have enough binder to use earth as a construction material. So I come again with the content of the soil used as a construction material. We have a binder and a granular skeleton. We'll see later, if we have too much clay, then it's not possible to compact the soil because there's not enough space for compacting. So a way to improve the behavior of during the process of manufacturing is to add some grains, and those grains could be crushed concrete. And why? Because you have some advantages, because you can use some high clay content earth, which is quite a lot of soils actually in different places of the world. So you decrease the clay content by adding some crushed concrete, for example. And also you don't need to care about the quality of the aggregates, the crushed concrete, because the expectation for compressive strength for earth construction is 2 megapascal, you know, so it's 10 times less than concrete. So this is why it is important to understand what is earth and architecture. And the problem here is not the mechanical aspect of the crushed concrete, not really the mechanical aspect of the material itself. It's how to process it and how to choose the right architecture. So of course, I saw one drawback is then if you have some polluted soil or polluted crushed concrete, then you cannot use them as a construction material, because as I said, this material is going to be very porous, so there will be some exchanges, some mass transfer, so it's not possible to use polluted materials. Okay, so now I'm switching to how to manufacture earth as a construction material. So you can find soils in different places, and this is a manual implementation. So you take the soil from a quarry or from a site or from excavation work, and then you mix it with a mixer. Why is it important to mix it? Because then you improve the homogenization of the material itself, and obviously if you add some crushed concrete, then you have to mix, but also to homogenize the water content. And then when you get the optimum water content, you can compact the soil in between formwork in case of rammed earth. But as I said, there's some different techniques. Yes, so you can compact, and in this slide, you see the manual implementation by a worker in between formworks. The formworks are steel formworks. They are similar to concrete ones, although stronger. And the compaction is made with a pneumatic rammer. You have different process. You can do it by hand, only by hand, not a pneumatic rammer, or you can also do it without a worker, with an automated system. Okay, and this is the completion of the walls. And then the strength, in this case, without cement, it's only given by the drying process. So the clay shrinks, the water is leaving the wall by the drying process, and then the capillary force are giving the strength. Once again, we can not reach very high compressive strength, but if you choose a proper architecture, you can easily build single family houses like you can find here. So, as I said, it is important to understand the architecture of building, because this is very important to be aware that it's different from the concrete architecture, the modern architecture that we have now. But there is a renewal of this type of approach because of the quality in terms of circular economy, in terms of sustainability. I will expatiate those aspects later. But now I need to talk about what is the vernacular architecture. It is important because we have a huge heritage. So it means that the economy is also important, because as we have thousands and thousands of buildings, we need to maintain those buildings. And this is Europe, but everywhere in the world we have similar heritage, cultural heritage. So do you see in Europe different colors? And these colors are just different type of techniques of vernacular urban architecture. Those techniques are different because they had to adapt the soils, because the soils are different. As I said, you need the clay as a binder, but some places you have a very high content of clay, so you cannot compact it. So the techniques are just adapted to the soils that we have. This is important because if you have understood the diversity of the vernacular architecture, you can be very strong to make a modern architecture that is smart, using the best way, using the soil that you have. And actually you can just improve this soil, to modify this soil by adding crushed concrete, or adding something else like fibers and so on. Or you can just use the soil as it is and adapt the architecture and the process. So the complexities is not in the material itself, is how to deal with the variety of this material. So this is a very different approach than concrete, where you try to standardize the material. Here is different. You try to adapt to the complexity and the variability of the material. So an example of the vernacular architecture, the people at the time, they didn't build vertically, they built horizontally. You can see the different process. You have here a barn, I think it's 200 years old, and they have only one formwork, a small one. So they move the formwork horizontally, and they are making the first row, circulating around the building. And when they have finished the first row, they go to the second one, and they can just remove the formwork immediately, because there's enough strength when you have compacted the soil. There's not too much water. It's approximately 10 to 12% of water content. So of course it has to dry, but the compressive strength is strong enough to remove the formwork immediately. And another example of vernacular architecture, I think this one is from the 19th century. This is not a single, it's not a dwelling, it was formerly a factory, and now it's been refurbished. And you can see on the first photo on the top that you cannot guess it's round off, but when you go inside, you can see the layers of the compaction of the soil. So now it has been refurbished as multifamily housing in France. Another example of single family houses in the center of towns. On the top and on the bottom, you can see a house with a vertical crack. So it's being refurbished and repaired to fill this crack and to ensure the wall stability. So this is still in France. So I'm switching to the modern architecture. So the modern architecture is different. You can see here round earth and timber frame. So I will explain the process of building. So this is another example, but it's the same process. So the walls are built vertically with only one formwork for all the walls. They are all independent and they are stable themselves. You don't need to connect them during the building process. But when the walls are completed, then there's a timber frame on the top. And this timber frame is interesting because it can connect the walls, and actually making some walls that are not connected formally means that you can build the walls where you want to build. For example, in the north face of the building, usually the architects are not building round earth because round earth is not a good insulation material, so they are going to choose another one. So it's a composite approach of the architecture to use the material where it's best used. It could be also useful for concrete, of course, but the approach is important as well for round earth, because we want to avoid the insulation because of the cost of the insulation, also because of the cost in terms of embodied energy. This is another example. This is a primary school. Also, you can see the walls are built independently on a concrete foundation, and those walls are just drying. So now, why it is interesting to build with earth? So because it can be energy efficient and it can be also very healthy material and therefore buildings. So we are targeting a very good indoor air quality, we have very good comfort, but once again, architecture is very important, not only material. We can talk also about social fairness, circular economy. The cost can be very low as well, but it will depend on the context and the process of manufacturing the materials and the content of the soil as well. And also the energy can be very low to build those buildings, but we need to talk about energy in use and embodied energy, both, because we want to have a low energy in both cases, in use and during the manufacturing of the materials. So there's always a challenge between there's a challenge for reducing energy, because it may be very easy to have a very low embodied energy, but you may have a very high energy in use. So actually what is going on now? We have some buildings with a very low energy in use because of the quality of the insulation, but as there's a lot of insulation, there's a very high embodied energy. So it's not very good. In the past, we had vernacular architecture, almost no embodied energy, but very high energy in use, because you cannot, they were not designed with insulation. So now within the modern architects have to deal with this challenge to reduce the embodied energy. That is possible with using earth, because you are using a natural material. So it's possible by definition. So now I'm switching to the energy in use, and this is a comparison between different type of buildings. I'm going to talk about the x-axis is about the time during a day, and we have on the y-axis the temperature inside a house. And we have different houses. Each color is dealing with one type of houses. And the green one is the temperature of the air outside, the outside temperature, the outdoor temperature, sorry. And we have 4 different types of buildings. And I must say that this study was made in Chile, in South America. And this is a very nice climate for earth construction, but it's just to show you the potential of urban architecture. And those buildings were very low-cost buildings in a very poor village in a specific climate of Chile, once again. So those comparisons are very interesting, and you have very low-tech buildings, and you can see the different temperatures. So this is a summer temperature. So in the morning at 7 o'clock, you have 18 degrees green curve, and around at the end of the afternoon, then you can get 33 degrees. Different type of buildings, the concrete block, and you can see that you have a higher temperature, and the best behavior is the Ramdorf one here. This is almost a perfect buffering of the temperature during the day and night. So the temperature is almost 27, 28 degrees without anything. There's no insulation, there's no technique, there's nothing. Okay, it's very simple architecture. But using thick walls with local soils, only Ramdorf, then you can get a very good buffering. And you can see all the other curves, they are not buffering the temperature as the Ramdorf is doing. So this is during summer. You can see that the inside temperature is, well, it's quite hot, but it's not too much. And actually there's no air conditioning as well, of course. But if you don't use this architecture, you can be very hot inside, indoor of the building. So the next slide is about winter. And same process in the winter, of course, it's colder, and you can see the green temperature, the outdoor temperature can go below 5. And of course, below 5, there's no heat as well, because I said it's very simple buildings. And once again, here, the best behavior is the Ramdorf house. That can buffer the temperature. And of course, in winter, it's colder, but we can get 16 to 17 degrees inside the house. This is an almost perfect behavior and zero energy. We can achieve that in Europe with a very smart building, but they are very costly in energy. And usually there's a lot of problems still with the architecture, the complexity of the architecture. So of course, this is specific to this climate in Chile, but it shows that the potential of very simple architecture, but a very adapted architecture to the context. The other side of building with earth is about the embodied energy, as I said previously. So we can compare Ramdorf, concrete blocks, masonry, and reinforced concrete. The embodied energy with Ramdorf may be, in that case it is, 4% of the reinforced concrete energy, embodied energy. This is for 1 square meter of a wall for a building, right? So you can see that the improvement is not 1 to 5 or 1 to 10. It's even more than that. So this is very impressive. And we always, oh no, sorry, yeah, okay. So the other side of building with earth, sometimes it is costly because you need more work and in terms of person hours. So in Europe, actually we have 2 crises. We have the climate crisis, then we have to reduce the energy consumption, and we have the unemployment crisis. We have to increase the employment. We need to give people work. So around building with earth may help on both sides. That's why people are now looking for this urban architecture more than ever. But it's still a niche because there's still a lot of barriers, and I will talk about the barriers and obstacles later. Well, I'm looking at the time, I should be good. So this is the circular economy context. Usually when we are talking about the circular economy, we refer to the Ellen MacArthur Foundation, but not only, because now we are seeing a lot of new publication on that matter. So you have different way of presenting the circular economy. Previously, in the previous presentation, we see the 3 R's: the reuse, recycle, and reduce. Yeah, but actually, yes, there's a hierarchy between those 3 R's. It's better than reduce than reuse, and so on. But here, okay, we can see design out waste and out pollution, and we need to keep these materials in use and regenerate natural systems. Well, I'm not going to spend too much time on that, but I prefer to spend time on some examples. So the Ellen MacArthur is giving some indicators, but I'm just presenting that for the vocabulary. Okay, we are talking about feedstock. So where does the material come from? We're talking about reusing, recycling, and the recycling efficiency. Okay, and we need to be aware of the destination after use, which is quite new. That's the principle of the circular economy. So after the end of life, what will be the fate of the building? But of course, in this seminar, we are talking about the end of life of the concrete. So that is very much in in the topic. So of course, if you use earth, you can get more than 100% circular, because those indicators were designed by the Ellen MacArthur Foundation, and they were designed for the manufacturing industry, not for the construction industry. So I'm going to talk about the first example of a 2,000 square meter office building in a town center in Lyon. So first, the soil the earth was taken from an excavation work nearby the site of the construction for the building. So it means that it is waste already. So we are taking waste from another site, okay? And we are storing this material, this earth, in the site of the construction in the town center of Lyon. So you can see the amount of earth that we are going to use to build. And this is the building, the completion of the building. So now the load-bearing round earth is completed. And this is an office, a building, and there's not the finishing yet. You can see also the timber frame, it's done the slab, but all the round earth is load bearing. And this is the finishing ongoing and the completion of the building. So that was the first example. And the second example is a single family house. It's a vernacular architecture. So we have been starting from, in the previous example, we start from waste. We use the waste, and then at the end of the building, we can reuse the material, because simply we have only earth. So we can just wet it and get it back to the manufacturing process. So here it's a vernacular architecture. So the soil at that time was not waste, it was extracted from the site nearby. It was not a waste. They dig the soil for the foundation, and then they use the soil. And when it's finished, the end of life of the vernacular architecture, well, it's simply returned to earth, and there's no waste. Okay, so it's a circular economy as well. So I need to conclude now. For the urban construction, the scientific challenges as currently addressed by the researcher. There's an increasing amount of new publication on that. There's also quite dynamic research by the RILEM Technical Committee. In the RILEM frame, you may know about the RILEM. and there's one technical committee on Earth that is concluding next year. And I believe that using Earth can solve the housing shortage in some places of the world, but there's a lot of limitation, as I said, so that you cannot build very high building. But most of the barriers are not due to the mechanical aspect or the pure scientific mechanical aspect, but there are more problems on the policy aspect, social, organizational, and cultural challenges. So, for example, and that's my concluding remarks as well. All the obstacles now were summarized by one study, but that's not all the problems. Okay, it's just a view because it's the only paper that we have on that topic, and it's dated back to 2013. So we have different type of obstacles. We have sharing mechanisms obstacles like problem of policies. We have processes problems like different accounting methods, and we have also economical problems like perceived higher upfront costs, payback periods, and so on. And of course, we have problems with the author called underpinning knowledge because of the problem of education, experience, problem of coordination, and so on. Okay, and then I would like to conclude with a positive citation idea and positive project in France. We call it a national project. In French, it's Projet National. Is starting next year, hopefully, and is going to deal with those aspects of social, economical, and cultural barrier. Actually, what is the national project? It means that the government is driving a project involving all the stakeholders in the national frame. Okay, I think I've been in time, and I'm not sure if I have time for question. However, thank you for your attention.
Okay, thank you very much, Professor Jean-Claude Morel. I think